Second note is to extend. Once you do your work, have the fundamental result. And for engineering, of course, we want to extend to many possible situations. So that is the purpose of the note 2. And note 2 is this, from the result, we have, let me rewrite, T, based on that equation, it is G beta J, and this is for J equal to how much? 3 BH cube. So B is the length side, H is here. So basically here for this case, we rotate. This one is we twist this shaft in this way, and then the torque can be related to the geometry. The beta is the angle of the shape. We have this result, and we can apply approximately and also the tau max is here. Okay, so those are the results. As indicated. And this application is approximation, approximations, but those approximations can be good. For example, the first one is this. If we consider a cross-sectional shape like this, okay, so if we consider this shape, and you can see the feature of the shape, basically you can see that can be decomposed into the superposition of three thin rectangles, right? And so for this case, if this one is under torsion, for example, this is a cross section, the torsion applied here. So this one is under torsion. We want to study the twisting of this case. We can use this result. For this one, you can see, say, let me put some dimensions. Say this is the B1, H1, and this one, for example, approximate B2, and this one is H2. And for this one, here is B3, and here is H3. That is a geometrical superposition. So in this way, the total J will be equal to the summation of, let me say this is 1, 2, 3 pieces, and that is I equal to 1 to N, and say 1/3 of BI HI cube. Depends on how many pieces you decompose. We just sum them together. So for this case, once you have J, then you can predict. Therefore, the beta will be, by definition, is the angle of the twist per unit length. And this is L. So for example, if this would be protruded from the board and by certain length L, you can predict this unit twist angle. That one basically is equal to T, equal to divided by J. That's it. T is a number that will be given. And you can calculate those, the J, and that is a geometrical information.
Shouldn't there be a G mentioned?
Oh, yes. G. Yes, thank you. Okay. This is the first result. And the second result is the maximum stresses location of the maximum stresses. Where?
Top and bottom, and left and right, and top and bottom.
Yeah, so we can evaluate, could be here. That will be here, here, and here. Okay, so that is the locations. And the other example is this. If we have a the serine, make a circle. This is and here has a break. Okay. So for this case, there's a small gap here, and like a serine. So for this case, you can see, let me say the dimension from here to measure to here. Let me call that is a B, and the thickness is H. So for this case, the J will be equal to 1/3 B times H cubed. And if this one, again, under the torsion, then divide by this, using this quantity, you can measure the angle of the twist. So from here you can see this one, the shape of this one to the shape of this one, basically in mathematics, they call it topologically equivalent. Basically, you stretch out the equivalent to a string, a very thin string of something. And that one, as long as that shape is equivalent to according to this category, we can apply. Are we okay? So this is, I think in our textbook also address this issue. You can read them. You're supposed to read them. Okay, don't just listen to me. My story is come from the different perspective. This one won't be the same as described in the textbook, but you can read there how the authors describe these issues. We pretty much there, and one last thing before take a break.